Okay, thank you. Thank you everybody for joining our workshop. I want to say that this is work of many people that made it happen. So we had this idea and we talked about it in several workshops before. And we think that is great opportunity now to do that online. Maybe that's a good part of the COVID that, we moved more to the online ways of working. So why we want to do it? What is the reason that we think this kind of workshop is very useful for people? Is that serverless is growing and it is gaining on in all areas, and both academia and industry, I think, are working more and more on serverless, and we should be more exchanging ideas and then learning about both what we are doing, but maybe also finding the ways that we can collaborate together. There is so much going on right now compared to like serverless is about 8 years old. We started workshops about 2017, so about 5 years, maybe 6. And a lot of changed since then, right? So it's not only about function as a service, but it is also growing into other areas. And maybe that is the way that the cloud will be in future used. So how we can create that open forum, or how we can make it so we do not have like once per year or maybe a few times per year in some conference meeting, but we can continue collaborating and even presenting whole year. So what about kind of approach where we do not have like strict deadlines or time where you need to submit, but just share what you are doing, what you want to, the community know about. We have a mailing list, we have a Slack, we can organize Zoom workshops like this one, and then we can work together by just showing what you are doing, getting feedback. And also we are thinking maybe a little bit of structure. So like today, like talks, but also if you have some lightning talk idea that you just want to, ask community about, or you have some prototype you want to show, demo, and not just put on YouTube, but you get some feedback in more interactive forum. And if you are doing PhDs or, anything else that is related to academia and also industry, we are thinking to invite people from open source projects and from serverless services that may be interested to reach out to academia. So that's our goal. And you can find previous workshops on all of them are online. You can find the talks, and we have now about 40 plus users in our mailing list and in Slack. We hope to grow that community more over time. And we really encourage you to ask questions, discuss anything you want to bring up related to serverless computing. And of course, we are organizing next like regular serverless workshop at the end of this year. So we hope you submit something there. And we are thinking to organize the next online version of the serverless workshop. That is to say that it will be not set date right now. It is based on what you find like time for it, or when when we have enough content to essentially make another online serverless workshop. Pedro, do you want to say a few words, and then we can transition to actual talks?
Yeah, no, simply explaining the community that we really come from this international workshop on serverless computing that has been collocated with different conferences. Next year, we go again with middleware in December. Probably deadline will be a little bit later, by mid-September. So this is what we are changing a little the slide. But this is peer reviewed, and it's like a classical workshop, whereas this WOSCx, we aim to be a different and more like agile version of the workshop, because this we do not have peer reviews, or you don't have to write an article. So it's really you have like something to explain to the community, and it will be very fast to reach. So we will try to grow this community both in academia and industry, because if you see now the agenda, Alec, you can move probably to the next slide. We really try to make a balanced agenda. So, and it's completely balanced, because in each session you will find like 2 academic talks and 2 industrial talks. And I think they are super interesting, because we have like both visions. Even in the steering committee in WOSC, we have the IBM guys, but also the crazy academic guys. So we are bridging the both worlds. In the first session, for example, we have like a senior staff like Alexandro, full professor at Brig University, opening this talk. But then we have Raul, from PhD, but distinguished engineer there at Dell, working in this exciting Pravega tool. Then we have Kyle Chad from Chicago, so again academia, you see, and then we have Alan from Lightbend, exciting industrial talk, and Kalix is really hot. So it's, I must say that I'm very interested in listening to Alan to see what they are proposing here from industry. And then again, in the second session, we invited also exciting people, again, 2 academics, 2 industrial guys. So we have Bologna, Antonio Corradi from Bologna, another senior academic. Also, we have Joseph Spillner, that it's also well known in the serverless community, and we have participated a lot in our workshops. But then we have 2 industrial researchers. We have Sebastian from Microsoft Research, presenting Netherite. And finally, Javier Picorel from Huawei, bringing his vision on serverless from China. So I really think the panel it's super hot and interesting, and let's go for it. So I don't know, Alec, I give you the floor, and probably we let Alexandro excite us all about the future of serverless.
Exactly. Please, Alexander, share your screen.
Thank you. Thanks for the introduction. Let's see if everything works. So at this point, I'm expecting that you can see my screen.
It looks good.
All right. If everything goes down the drain from here, then I've got 2 points. One, that there's this link with the slides. You can also, of course, find them in the shared folder. And the second is that I have a very quick overall message that says the following. I think if you start with a reasonable description of what serverless computing is or should be, then you get at the same time the beauty of it. So the part that we would want to love, and also the challenge of it, the difficulty of it. So the part that we actually have to make work before we can indeed learn to love serverless computing. And I want to thank all the organizers of this workshop. I find this an amazing initiative, and Pedro in particular, really many thanks. Okay, so let me get started. My pitch starts with a very simple observation. I'm a scientist. I look at the world around me. A lot of it is digital, especially in the pandemic period, but for me now as well. And I'm noticing that with so much being digital, this is really the golden age of, well, computer ecosystems that actually make work all these important parts of our daily lives. So from education to big science, we're already accustomed to big types of computation with lots of people involved in various ways. But of course, in the last, let's say 3 to 5 years in particular, we've seen not only the emergence, but also the growth of digital governance. So pinning, identifiers, even the police is working on such systems these days, of big business critical workloads across continents and data centers. Of infrastructure management done really right and automated, of video streaming for movie watching, for all sorts of other things, gaming and safety and security. And one of my interests, pretty much modifiable virtual worlds, which support online gaming, but also digital twins of matching reality with digital copies that allow us to understand various things. And how do we make all these applications work? Well, we know already that the technology that supports networking and transferring data has improved rapidly, and there are really interesting things on the horizon. So we're already beyond 5G, although we haven't deployed it everywhere, I don't know, terahertz and a lot of other things. But in terms of computation and data processing, we still have a lot of the terminology and technologies that we've actually been used with for the past 20 years. So cloud computing as a successor of grid computing, perhaps a bit the emergence of edge computing, the big data center, all these things keep staying in the mix. And what happens is that as we're trying to make all these applications really grow, really develop, really get all the properties that we are aiming for each of them, I can go on and on about the workload characteristics. It seems to me that we've forgotten that actually the technology in which we build the initial applications that I've enumerated so far is actually quite brittle and should not be taken for granted. So if we look for the simplest kinds of applications, Pokemon Go springs to mind as an example of a trivial game with just a few hundreds of millions of users worldwide. The availability of these services, of these gaming services, is not great. What availability actually means can be debated, and I'll return to this point that the semantics even of what we are after are not well defined. But we already know that the availability is not good. There are other interesting phenomena. Performance is eternally an issue, especially with the applications that need to be more interactive or respond quickly. But what you typically start seeing is that now performance and dependability in all its senses, availability, reliability, start forming a sort of a continuum. So simply focusing on one or the other with different teams is not something that promises much in terms of a solution. And in the last, I would say about 10 years, we've discovered that at the scale at which we're operating our serverless operations, but also other kinds of IT operations, we're starting to have real impact on the planet. And that has not been always the case, or at least not one of our main concerns. If you look at the power consumption or release of different pollutants, or even water pollution, then these are major concerns for the current technology. So in this talk, in a nutshell, I want to tell you that serverless, for me, it's a notion of really extreme automation. If it's trivial automation, then I don't find it serverless much. I find it previous cloud or other 70 years of automation in computing. And one of the things that makes this extreme automation really difficult is that we want to be able to report with fine-grained accuracy and detail what is happening in the deployment over the course of running these serverless applications. And we want to be able to bill in a way that is utilization based. And that is actually very difficult, because as soon as you make things utilization based and you link them to economics, real pressures from the market and the society start to appear. So a lot of things need to really be optimized, not only that they should run, but extreme automation should really move into automation. So it is a deep belief of mine. I don't have proof at this moment, but I think the evidence of everyday practice shows it, is that serverless can really be achieved only through rather complex and smart computer ecosystems. So the notion that we will build something simple that will just run serverless, I think it's illusory. We want to do this for the user, but whether we can do this as computer systems people, I find this rather unlikely. So I think we are heading towards really high complexity, and we will need to have a lot of parts that take decisions without necessarily us directly involved as the humans. And I have a little analogy here. It turns out that other sciences have discovered that simplicity in any part of the modeled environment is nice, but does not actually allow you to answer big questions. And climatology, for instance, for about 150 years, did exactly this, modeled really small particles, but were not able to actually predict heavy weather. It turns out that when you take these different models and you couple them, and that can only be done with a lot of computation and a lot of complex modeling and a lot of complex operations, only then can you actually explain whether these two different systems will actually merge and form a killer storm, or they will just dissipate nicely. And we have exactly the same thing happening for serverless operations. I've mentioned all kinds of digital services. They form workload, which over time can be higher or lower, runs on typical infrastructure or diverse infrastructure. But the main point here is that for any click that a Pokemon Go user or a Netflix user or Dropbox user or any other digital service user issues, there are actually hundreds of services that form an ecosystem from authentication to actual execution. And these services run on the many computers of one or several data centers, and they need to be properly managed and scheduled to actually get a system that has good performance, high dependability, is sustainable, etc. So what do we do about this complexity? Well, whenever there's complexity, computer systems people invent a layered pancake architecture that at least breaks down into modules the different operations. We've done something like this ourselves. And here what you see is one of these layered pancake architectures that we extracted from common practice. So we looked at tens of different serverless platforms and tried to identify what are the main components, how they interact, etc. And what you see here is that at the time, so that was 2019, full 3 years back, we were looking at functions that get coordinated and composed in various ways into workflows. Turns out workflows are a major component of how to make a proper serverless run. But this layered architecture is actually a subpart of a much larger architecture. Here, for instance, for even the simplest, well, not the simplest, but a reasonable application in either AI or ML or deep learning. This one in particular, I'm going to exemplify it with ML. What you see is that there are actually multiple programming models combined in a much more complex workflow, where the actual functions that get executed to form an application are these little boxes. And these boxes, when they execute, they really engage many different layers of a much more complex reference architecture. In 1 minute, I will end.
Thank you.
And we need to make all this stuff actually run and actually work. And it gets more complex than this. This is actually the reference architecture that I would expect in a data center. But actually, we don't have only data centers. We have data centers and edge points of presence and even endpoints. All these things have different parts of the stack that are actually composed at this point of many different kinds of technologies that are not really compliant one with the other. All of this stuff should work if we want to write and create applications that easily can be deployed across the computing continuum. One other point of attention is for me that if you want to make this stuff work, then you need to actually reason about it before you've built it. Then it's too late. So how do you do this? Well, for any other infrastructure around the world, we actually construct it using simulation models. So I think that's one of the things that we will need to add into the mix. Okay, 30 seconds to end. I've mentioned that there are all these different, more modern concerns of what we should do with serverless. I don't have time to mention all of them other than cursorily. So one is that the metrics that we want to capture are really much more diverse than we imagined. They're not the traditional performance metrics. We've written extensively about it, so I hope this would be useful. We keep hearing about auto-scaling. It's only one of the many operational techniques. The community has not yet explored even a little bit of this enormous construct and interrelationship of operational techniques. So the take-home message, I think serverless means extreme automation with fine-grained reporting and with utilization-based billing. The serverless ecosystem is really large, has really many goals and many different approaches and really many challenges. So I'll learn to stop worrying and love serverless computing once we actually meet at least many of our goals and we overcome many of our challenges. Really, many thanks for listening. I think I should stop sharing the screen for now.
Thanks a lot, Alexandro. So nice. All the layers that we create are amazing. I see. I don't know if we should remove or add more layers. So but yeah, it's impressive. So Raul, I mean, now it's your turn. Go ahead with it. So you can share and start your talk. Thanks a lot, Alexandro.
Yeah, I'm going to share my screen. Can you see my screen now?
Looks good. Full screen.
Yes, good. Okay. Okay, so hi everyone. My name is Raul Gracia. I'm principal engineer at Dell EMC, working on the Pravega project, which is an open source storage system for data stream. And I'm going to give this talk about data streams, auto scaling of streams, and its connection with serverless computing. So not much to perhaps nothing new for you probably, but serverless computing and data streams are a great match. Serverless frameworks provide us like the ability to trigger functions in response to events, and they provide a great deal of abstraction of the underlying infrastructure and a simplified programming model for users. And at the same time, we have data streams that are, conceptually a continuous source of events, which looks like an ideal input for serverless computing frameworks. And we have to take into account that data streams are becoming a first-class citizens abstraction for many use cases in the real world, in customers, such like objects or files. And one example of this synergy between serverless and streams is that we can see out there, it's frequent to see serverless frameworks like OpenWhisk or Lambda having connectors or allowing you to consume messages from Kafka, for example, right? And the popularity of data streams and serverless, right? So for example, at Dell EMC recently in Apex Private Cloud, which is a new offering from Dell, we are now able to deploy Knative as a service, right? So it's just like another data point of the popularity of this kind of computing model and how it can actually solve problems in real customers. We have many of them that are use cases that are working with the streaming data platform, which is a product from Dell EMC, which is providing streaming storage with Pravega that I'm going to introduce next, plus analytics, right? And we can have we have multiple cases that data streams made of drone images, video analytics, and sensors, IoTs in factories, and perhaps not all the use cases, but many of them perhaps could be solved or addressed easily with serverless computing. Of course, here I'm going to focus more on the source of data for serverless framework, which is Pravega. Pravega is a storage system for data streams that is an alternative to Apache Kafka or Pulsar that perhaps you are more familiar with, and it has like several distinguishing design decisions that makes it like a brand new system that offers like different capabilities to existing counterparts. So let me introduce Pravega. We'll start with some concepts. So again, Pravega is an open source storage system to serve and store unbounded data streams, and which is basically an abstraction that is an append-only sequence of bytes. So data in a stream cannot be modified, but it can be truncated. And then we have writers, which allow us to, and readers that allow us to write and read data from Pravega streams. Of course, we cannot have an infinite piece of data, right, for a stream. So basically, in behind the scenes, internally, Pravega splits a stream. The abstraction of a stream is built into segments, which is the basic unit of storage in Pravega. So basically, a stream can be understood as a sequence of segments. Segments can be in two states. They can be open, or which means that we can write data that can be consumed by by readers, and or segments can be sealed, which means that they are read-only. One of the distinguishing features of Pravega is that it is a tiered storage system, meaning that Pravega is designed based on the assumption that you want to keep your data forever, right? So in a cost-effective way. To do that, Pravega has a tiered design. So we have two storage tiers. When a writer writes data to Pravega, we first write it to tier 1, which is a distributed write-ahead log, which provides low latency and durability of messages. And asynchronously, Pravega is grouping those events into larger chunks and moving them into what we call tier 2 or long-term storage. And so basically, we have low latency tail reads for applications like serverless frameworks consuming those events. And if we want to do a batch job on that data, we also achieve high throughput. One more important characteristic of Pravega is the write-read parallelism. So basically, in Pravega, we can have multiple parallel segments to write data to and to read data from. And apart from that, another challenge that Pravega solves is to provide write and read guarantees. These are extremely important for making sure that we are not missing data or we are not losing events, and at the same time that what we read at the other end is consistent. So Pravega provides exactly one semantics. There are no duplicate events or missing events, even though there are reconnections, and total ordering of events per routing key and per writer. And at the reader side, we also guarantee that there are no duplicates, no missing events, and so on. So this has been like a super quick overview of Pravega. And just to wrap up, so why Pravega compared to other streaming system or storage system for streams to consume data from is that it provides unlimited retention from its design. It allows, with the same system, it handles real-time analytics and batch analytics. It provides data durability, parallelism, and guarantees for reading and writing data, right? But in particular, because in the previous talk we heard about scaling and so on. One distinguishing characteristic or feature of Pravega is stream auto-scaling, right? Of course, I mean, in a data stream, we cannot assume that the load is going to be constant. There would be load variations on a stream, daily patterns, and so on. So ideally, a data stream should basically vary the parallelism of the stream, the number of parallel segments accordingly to the load, right? So this is a feature that I am not aware that any other system has, which is auto-scaling. In Pravega, we can define stream policies, scaling policies on a data stream, such as if a segment gets more than X number of events per second, then we split it. And basically, Pravega tracks this with a feedback loop and automatically triggers scaling up and down segments. So this is a kind of conceptual representation of that. You can see in the image the key space of routing keys, which goes from 0 to 1. Initially, this stream has a segment 0, which is a single segment that is handling all the load. And after some time, the system detects that this segment is becoming hot, so it decides to split that into segment 1 and segment 2, which are basically getting half of the key space each. And as you can see, the process continues until it stabilizes, right? This is a real view of what it is stream auto-scaling in Pravega. We induced an experiment with a variation in the number of events per second we were writing to a stream, and this is the lower graph that you see representing the load. The upper one is a heap map representing the parallel segments at each point in time of that stream, and the color is the load, right? So you can see that when the load goes from higher to lower in the middle region of the plot, the number of parallel segments is reduced, and when it goes up again, we can see again splits of segments into multiple ones, and then we have more parallelism of this stream. This is done completely automatically. Neither the application or the client it realizes about that. So then I wanted just to try to connect the dots just to complete the presentation, right? So on the one hand, we have serverless frameworks, which are easy to use, very popular, and they take care for us to scaling up and down computing instances. Some of them, perhaps, for example, would be based on resource metrics like CPU. But at the same time, we have now data sources like Pravega streams, which can vary the parallelism of a stream along time, which is a new software-based metric that can be used to scale upon, right? So the idea that I wanted to share with you here is that perhaps we could explore, if that would be interesting to use the parallelism of a Pravega stream as a hint or as an additional metric to inform the serverless computing framework in order to be able to scale up and down, in this case, based on this new software-based metric. This idea is not new because we already have a success story for Pravega and Apache Flink. Today, we can basically automatically scale the parallelism of an Apache Flink job based on the number of parallel segments of a Pravega stream. And I thought that could be interesting to start an exploration whether that would make sense in the context of serverless. So yeah, that's it.
Thank you. Kyle, you are next speaker. Can you see if you can?
Yep. Can you see my screen?
Yes. Yes. Thank you. And go to full presentation mode.
Yep. You see it full now?
Great.
Okay. Well, thanks everyone for the invite. Great to see a big community here. I really am a big supporter of this serverless effort that's going on, particularly led in Europe. So I'm going to talk a little bit about some of our work recently on what we call Federated FaaS. This is a project that we're working on at the University of Chicago, Argonne, and the University of Illinois. There are many people involved. I'm sure I missed several of them there, but those are some of the key contributors. So our focus in our group really is on scientific computing. We work with scientists spanning cosmology, biology, archaeology, all sorts of different sciences. And as we've started to support them over the last decade and work with them on various things, we've started to make some observations that I think have led to some of our interest in adopting the FaaS serverless type model for science. And so these are sort of three categories of trends that we've noticed. And I don't think these are going to be surprising to anyone here. But the first is that resources are becoming increasingly specialized. And that's in part because of the slowing of sequential processing power, the end of Moore's law. We're starting to see much more diverse hardware infrastructure. It is also, of course, due to the changing workloads, AI accelerators, et cetera. And as we see this sort of growth in the specialization, the types of hardware we have available, we, of course, are seeing more distribution. And maybe we see that because I'm a distributed computing person, but I see, like Alexandru did earlier, that this continuum of computing devices that are accessible now to researchers, and the challenges, of course, of being able to make use of those resources in an efficient or effective way. On the workload front, as we just saw, we're seeing a lot more sort of streaming workloads, interactive workloads, a lot more machine learning workloads. As Alexandru pointed out before, much more fine-grained tasks. And the interesting thing is when you look at an application, you might see that the various components may well be best executed in different places. If we're running some sort of large materials simulation, we'll have CPU resources for, say, the more legacy simulation codes. We'll combine that with AI resources for optimization, et cetera, for steering the simulations. You see there at the bottom some pictures of runtimes of some functions that we measured in various scientific applications. And then the third thing we're seeing is that the community of users, scientific users that are trying to engage with these workloads and these resources is becoming increasingly diverse. We're seeing people try and apply notebooks. They want sort of custom or sort of environments in which they're familiar to be able to drive their scientific computing workloads. And so when we look at these requirements, we start to think about how FaaS and serverless can help address some of these requirements. And I completely agree again with Alexandru about there's a lot of sort of system stuff that's potentially impractical to actually address all of the problems. But if we think from a high level, we're going to think about what would we really like. You imagine a serverless model, we don't have to worry about the infrastructure. Well, we can support very granular tasks, and we can provide an abstraction that's actually easy to use and easy to understand for a very diverse set of users. So if we look at what we see in the current world of serverless, I'm just going to move that out of the way. We see it being led by cloud providers. We see on the right there a list of capabilities that are provided that I think make serverless particularly attractive to users: the single provider, a single interface, a reliable, robust, highly available interface for which we can define our functions and run our functions. We see a homogeneous execution environment abstracted with container technology, etc. We see this transparent automation, elastic execution of even the very smallest tasks. And we see integration with cloud provider data management systems. So as a user today, probably 99% of users are engaging in a way like this, where they're running their functions or on a particular cloud provider, or perhaps on an open WOSCx or some other open FaaS deployment that they've deployed locally on a Kubernetes cluster. If we look again at the scientific computing ecosystem, we have a bunch of computing devices that are distributed all over the place, from sort of hardware, AI accelerators, supercomputers, instruments, edge devices, et cetera, et cetera. But of course, our scientists and we as systems people would still like to provide this sort of single reliable interface. We'd like to provide a homogeneous execution environment where we don't have to worry about hand wavy here, the specifics of actually being able to run things on different types of devices. We'd love for it to be completely transparent, for it to be automated, for it to be elastic. And we would also like, of course, and this may be even more of a dream, although Raul's talk maybe ties in here quite nicely, is ways to integrate this with sort of wide area data management, so that we can have sort of common views of the world in terms of data. And so what we've been building over the last, I don't know how long, maybe 3 or 4 years now, is a system we call FUNCX. And this system aims to sort of mangle together a federated distributed world of computing infrastructure with the sort of cloud hosted functions as a service serverless type model. And so what we have is we have a service that's run in the sky in a cloud environment that's hosted, that users can communicate with. And then we couple that with these distributed endpoints that are deployed on different computing resources. So you can deploy an endpoint on a laptop, on an edge device like a Raspberry Pi or a Nano or something, on a supercomputer, on a cloud, or anything in between. You see on the right there, basically from a user's perspective, they speak entirely to this cloud service where they register their functions as they do with any other serverless FaaS system. The difference is when they come to invoke that function, they need to pick where they want to invoke it. So they need to choose an endpoint on which to run it. The good thing there is that the cloud service basically provides a sort of fire and forget model where it caches the invocation of that task, the call of that function, waits for the endpoint to be online, goes and runs that task on the endpoint, and then caches the result back again so that when the user can go and retrieve that result when they need to, or they can register for asynchronous notifications to get results back as they are completed. So I'm going to just briefly on this slide, in terms of architecture, we have a cloud service here that's basically running a database of functions. We're working on a container service for building out different types of containers. Of course, Docker works great in cloud environments, but in many of the HPC environments, we need different types of containers. So we're building out at the moment a service here to create different containers. And then we have this ecosystem of endpoints that are deployed, where these endpoints are basically their own little function execution system. They keep a queue of tasks to be able to run. And so the cool thing about this type of environment is we can start thinking about different layers on top around how we choose where we execute functions, because of course we may want to execute a function where it's close to data, or where it's cheap to run, or where we might get resources more quickly than we otherwise would somewhere else. And so there's a real opportunity, I think, there around the scheduling side of serverless applications. So I thought I'd end with just a couple of examples of where we are applying this type of model. As I grouped into 3 sort of common canonical use cases. The first is people who want to run fire and forget execution, typically a bag of tasks, perhaps a somewhat simple workflow. I come from the workflow world, and interestingly, our workflow system is primarily used by people to run bag of tasks. So the sort of FaaS model maps very nicely to what I think a large percentage of the workflow community are actually doing. So typically what people want in this fire and forget model, they want to execute tasks remotely. they would like to outsource that complexity. We have one person running a million tasks. He would like to just queue up those tasks, run them when he gets allocation on a particular machine. He would like to be able to move those tasks between different machines because people have different allocations on their campus cluster or on an HPC system. And they would, of course, like to elastically scale to use resources as they make sense. So some examples down the bottom where we're doing ML-based drug screening of COVID-19 therapeutics, where we're doing statistical inference for high energy physics. The second canonical use case is automated analysis of data, and I think this speaks again to both the previous presenters talking about sort of event-based computing. And so we've done a lot of work here where people would like to basically tee up tasks to be executed, functions to be called as a result of data being acquired from an instrument, or as a result of perhaps a new model being trained and needing to rerun a bunch of inferences over data. And so what we'd like to do there is basically automatically process data as they're required. We'd like to be able to integrate with data sources, event streaming sources, Globus, et cetera, for where data currently live. And we'd like to be able to execute functions across the computing continuum, anywhere from where the data are actually produced in the instrument through to perhaps a large scale system for analysis. So we're doing a lot of this with various beamlines at Argonne's advanced photon source. And on the right there, an example of training and then deploying neural networks at SLAC. I can't see the chat, but I'm assuming that one message means I'm down to about 1 minute left. Tell me if I'm wrong. The third common use case we're seeing actually is that a lot of applications or services that people are building also require these types of functionality on the back end. So providing a sort of robust API-based service via which people can integrate is advantageous because they can outsource a lot of the complexity of being able to actually run different functions. So two examples here. The Data and Learning Hub for Science is a system we've built for registering and publishing machine learning models. And of course, the advantage of tying in the FaaS system is that we're able to then provide on-demand inference of those models for users as they see fit. So we've sort of released the system as a bit of a prototype. We haven't really advertised too widely. Over the last year or so, we received NSF funding and we've started building out a more production implementation. We're now at a point where people are starting to adopt the system. We have several hundred users who have run, this is a few months old, this slide, but roughly 20 million functions, several 100,000 functions have been registered, etc. With that, I'll end. There's a website there. I think in general, the takeaway from my talk, I think much like Alexandru's, is I think there's a real opportunity for thinking about where the sort of serverless FaaS models can be applied more broadly outside of the sort of narrow view of a single cloud provider. Thank you.
Alan, are you ready to present?
Yes. Sharing my screen.
Looks great.
Okay, so my name is Alan Klikic. I am a solution architect at Lightbend. For those that don't know about Lightbend, Lightbend is a company also behind Scala, but mainly a company behind Akka. Akka is a development framework, actor-based, and it's already on the market for 10+ years. It's an open source JVM-based development framework that's proven itself during these years, solving really sophisticated the data distribution, high performance use cases where a lot of different big companies are using to solve these kind of problems, like PayPal, Tesla, and also Disney streaming, for example. But what we noticed during the last 10 years is that many of these developers are facing problems because of the skill sets to be able to adopt the framework and address these sophisticated problems. So we started to do 3 years ago, develop a platform as a service that we called Kalix. Basically, that's a generic developer-based platform as a service that should enable any developer in the end, backend developer, to build this kind of large-scale, high-performance microservices, but also addressing the skill sets regarding the operations, also to remove all requirements around the operations. So the goal, implement the same level application that you would do with Akka as a development framework, but not require that certain level of skill sets with bringing that platform as a service-based solution. So as I said, Akka main development framework and a product from Lightbend, but now build on top of Akka, Kalix. So Akka brings that a competitive advantage regarding the performance, efficiency, reliability, real-time data processing, scalability, and streaming. But again, for simplification, on top of Akka, we built a serverless runtime. Basically, it's fully managed runtime infrastructure that has a container-based deployment, also integration with CI/CD pipelines, and also embedded logging, monitoring, auto-scaling, and security. And with that, removing a lot of responsibility in the end from a developer and to be able to manage and also focus more on the business logic. Capability main, let's say, competitive capability that are offered on Kalix are basically Akka ones. So able to implement stateful based services. So where your state, you model everything around the state. But again, you need to know how to distribute that state. It's something that's handled by the platform. So be able to implement distributed data patterns, but without knowing how to do so, but just modeling your data structure and the flow. Also abstracting these different communication patterns, especially focusing on event-driven architecture, where these event-driven communication patterns are there as a capability, but wrapped in very simplified development model to be used. And also one of the two main also competitive advantages of Akka, to be able to build event-sourced and secret pattern systems, and event sourcing as one of the main enablers for event-driven communication patterns. And also to be able to address a larger community, because Akka is, as I said, JVM-based framework. So we wanted to address and be able to enable developers outside of the JVM community to be able to leverage these capabilities. So there is for now JavaScript, TypeScript, Java, and Scala support, and also working on having a Spring-based toolkit also for that, but also we believe much more will come. Just in few steps, how would you build this kind of service with Kalix? So as I said, our focus was on simplicity and heavy weight lifting done in the back. So first is an API description. So Kalix is API first, everything is described in the API. Then you need to choose a durable storage model. So you're just choosing the model, you're not choosing the store physically, but just what model you want to use. And the third is implement the business logic. So for now, as I said, for this API first development model, for description, Kalix is using protobuf. We are considering also other options there. And basically you need to design data structures for your endpoints. And also regarding the stream, and different kind of patterns can apply, like a streaming, eventing, and request response patterns. And also designing your persistence domain. So the focus is mainly on a data structure. So you don't focus on a database or implementation details, and also you don't focus about how you access the data, how you query the data. You just focus on the data structure, and everything else is handled by the platform. Choosing different kind of durable store model. So again, it's just part of this API description. There are some custom protobuf annotations that can be used to choose which durables model you want to use. So for now, we support key value one, a simple just storing the state based on a key, event sourcing, and also CRDTs. And this simple state model is just a question of a change inside. So that, as again, iterating that we emphasizing that we want to do things, enable users to do that in a very simple fashion. And in the end, writing the business logic. So I said it's a polyglot. Each of the languages has an SDK. Each of the SDK takes the API definitions and then based on that builds acquired resources, and then enables you to implement the business logic code. So in this case, we have an example of a Java code. You can see that the current state, basically the data of this car shopping cart, is just passed into your function. So basically it's injected inside. And there is no need to query and worry about how you're going to cache the data, how you're going to store, how you're going to distribute the data, how to handle the locking in the end, distributed locking. This is all handled by the platform. You just need to implement the business logic here on the level of that state. And depending on the that model that you're going to use, you're going to or persist an event, or instruct the platform to persist event, or in the end just save the state. A little bit under the hood. So yes, it's built on top of Kubernetes. So there is something we call an execution cluster. Execution cluster is installed on each of the regions of our supported cloud provider. So for now, we support AWS and GCP. So intention of Kalix is to be cloud agnostic. And there is a notation of a project that's basically an isolation for running your services. Each of the service consists of a state proxy. So that's a sidecar that is injected in parallel to your user code. So user code is your business logic that you have in. And the state proxy is something that is proxying all the requests that are coming in, enriching them with the data, basically handling the data, and then passing data to the user code. The user code instructs what else needs to be done with the data. So if you go a little bit deeper, so each of these services, of course, will be scaled. As I said, there is an auto-scaling mechanism for that. And for those that know about Akka focusing on actor model and having Akka cluster where you can distribute your actors and your state representations in a cluster. This is something now it's handled by the proxy, abstracting that implementation from a developer, because we found that that part is the most complicated one. And with this, we want to have that user experience and developer experience as best as possible. And again, here is the web page of Kalix. We just launched it a month ago, so it's you can try it out for free. You can do a trial account there, and as I said, if you have any questions, please let me know. And yeah, that's it from my side.
Thank you, Alan. So we have now a short break, 5 minutes. Please come back at 1 p.m. of Eastern time or whatever time is in your time zone. And please use Slack for asking questions, answering questions, anything you want to talk about. And remember that at the end of our workshop, we also have a panel and time for questions in Zoom. So if you have some things you would like to have discussed or bring up, keep it in mind. Well, post it to Slack first and then bring it up. So we have 5-minute break now. And then we start with Antonio talk. Okay, let's start the second session. Antonio, you should be able to share your screen, right?
Yeah, yeah, should be.
I can see it looks great. I will put 1 minute message when, you know.
Sure. Okay, yeah. Okay, so I am Antonio Corradi. I'm working at the University of Bologna. My department is computer science and engineering. Can you hear me? Yeah. So, can you hear me? Yeah.
Yeah, there was an echo for a moment, but it is good now.
Okay, good. So my talk is going to be about some consideration on what we have to expect from serverless computing based on the idea which is the model and which are the trends we can forecast. So the main idea, I'm just finishing a class on infrastructure on cloud computing and big data, and serverless seems to have as a word a lot of attraction for students, and not only. Even companies, when you speak about serverless, they tend to be excited about the concept. So what I'm trying in a few minutes to try to understand if we can try to forecast something about serverless trend, looking at what has been happening about cloud, especially in the direction of furnishing services in cloud, going into the area of multi-cloud and the area of cloud continuum that some of the speakers already touched. So the capacity of working in many different environments. So since the very beginning, cloud was providing mainly service-oriented architecture. So you define services and get these services. And you tend to rely a lot on synchronicity. And you tend to rely a lot on being very acid in the sense of being atomic, consistent, durable, and all those kind of things. And then your system enlarges, especially the cloud, and you start thinking about scalability and how you replicate the rest of the system. And now you can be efficient in answering your possible client. So cloud maybe have several layers, and they start working with the asynchronicity. So you are really relying on event. I'm not speaking of serverless at this point, simply cloud. And so you introduce MOM between different parts of the cloud, the different clouds, and so on. And since the system is enlarging a lot, you tend to use the cap theorem, in which you are stating that if the system is large, you can have only two of the three properties, consistency, availability, and partition tolerance. And since you want to be very efficient in answering, so you want to give fast answer, and you want to give have the possibility of working even when you have partitions in your cloud, so you tend to neglect consistency. And that's the important part, has already been touched by other speaker. So you have to automate everything to be very reactive. You have to keep in mind that anything can fail. And so you start working a lot about eventual consistency. And that's the main trend of multi-cloud, and even doing that in many situations in which you're working with the final IoT, and then you go into something in the middle, into fog or whichever, and you go into cloud. So let's go into our model of function, and the appeal of the function is the fact that you, as a user, you're really not worried about how the function are going to be executed somewhere, where they're executed, which are the resources doing it, and so on. So the function as a service is really a good execution model, and you can be at the very beginning very synchronous. You're asking for something, and your function is going to be gracefully delivered to you wherever they are and wherever they are in need of being. Our model, I'm not the only one, of course, working on that. We have a PhD working on that. He's visiting now there, in fact, Pedro, and is Andrea Sabbioni is following the workshop. So our main idea is, okay, let's try to make really a small architecture model with the idea of having basically asynchronicity, and using a synchronous pattern instead of something very synchronous. And so the idea of event, very intrinsic to into serverless, becomes something very intrinsic in all the components. So you may try to identify some components like an initial triggering by which maybe you can get your request, even HTTP or REST, and then you decide that there is a function to be executed somewhere. So the one in charge of that is going to be the function executor, and in the middle you have another small component we call controller in charge of deciding which are the resources you may give to your function when they're going to be executed somewhere. So this is a small example of the sort of workflow. It's common maybe to many possible architecture, but we want to make it a sort of a model, an architectural model for the support. So we can go a little in more detail than that. So you have again the idea of starting event coming from outside, and the trigger is capable of getting the event and translating into the controller need. The controller is the one deciding there is something to be executed, and maybe deciding which is the scheduling and when things are going to be executed by using which resources and so on. And then you have the real execution, and that's the function executor. But the executor can be eventually decomposed in other components like the triggering, the internal execution triggering the invoker. And the invoker is capable of defining which are the functions going to be executed and triggered at the end, which is the environment in which they have to be executed and so on. And of course, this model can really be capable of working whichever is the possible target environment. It can be either in a cloud or in something else, in the edge, or going back and forth. So that's the basic idea of our model, try to define small components that can be very flexible and capable of being, in general, configured and started and deployed where we're in need of. Let's try to go a little on. I don't want to give you too many details about things. So the main idea is you may have many functions very intrinsic to serverless computing, like function composition. So you can decide maybe you're having two possible functions to be composed together, one after the other. So you can add the trigger of one and the second trigger for B. And then you may have something in the middle, or simply a workflow connecting these four components. But you can have something more, not only changing the condition, but also defining a special function that is coordinating the execution of the two possible functions you may be interested in. So all those kind of things can become part of an architecture. You can use as a model for deciding a little better where these components are going to be working, how they can get possible input from the final user, the application, and going on and working whichever is the deployment you are choosing. So that's what we have, of course, and we have seen already examples of possible application in which you are using this kind of, or it can be modeled by this model. Let's try to go a little on with the forecast that we can make. So I think we all agree, being here, that serverless are really spreading. And so the application we have seen also today are really enlarging a lot, enhancing themselves in two dimensions. One is the real dimension of function. So the number of functions you are using is going to grow more and more. But there is also another possible dimension. The dimension is in time. So the life cycle of our application or our platform is going to be long and long. So making the example of cloud, okay, we want to have something capable of granting the services you're in need of. Not only the initial configuration, it should be very elastic, and then you decide on having the result you're interested in. But if you have something very large in dimension and very long in time, maybe you're in need of something else, because the long life for your system, your application, your infrastructure, your support need for something else. Since the life is going to be long, you should have something capable of being dynamic enough for changing while it's working. So you have to change possibly the function you have provided at the very beginning because the situation of the environment has changed. And maybe you have to adapt the configuration to something else going on, occurring while you have already started the application or in general the infrastructure. So more and more serverless should be capable of starting with a good way of configuring things, but at the same time reconfiguring things while they are in execution, so that the life cycle is going to be followed for the entire span of the thing. So that's simply a sort of a suggestion about what we have to expect from next generation of serverless. So I do feel like that maybe next step is going to be having the capacity of putting together many different platforms, different applications, in a sense, according to the idea of multi-cloud, multi-serverless, having different function as a service support capable of exporting components among each other. And that's going to be something very significant. And maybe we're going to speak a little more in the final panel about that. I think I can stop here, of course.
Thank you, Antonio.
Yeah.
Joseph, can you share your screen?
Yeah.
You will need to unmute, Joseph.
Yeah, sure.
So hello, everybody. I will continue the presentations with our work on real-time multiplayer gaming, which has been a student project. So two students, Evan and Rico, came to me last year and asked me to do a gaming project. I brought it into this context. And then through Alexandru, who has been a previous speaker here, I got to know Jesse, who was a PhD student in Amsterdam, working on game projects in the serverless space. So he agreed to become a co-supervisor of the two students. Now, unfortunately, the students are in final exams and have bachelor presentation next week. And Jesse, for other reasons, could not be here. This is why I'm going to present the work to you. So the idea has been to look at the requirements that we have in real-time gaming, which is mostly the real-time, right? So we want to see which kind of application can cope with real-time characteristics, or with the characteristics that are offered by serverless platforms in a real-time context. And the other challenge here has been multiplayer state exchange. So if multiple players move in a game, we need to exchange state, and we know that this is a bit of a challenge in the serverless space. So we have found that the two issues individually, both real-time and multiplayer, have been analyzed before by other researchers, both of them very individually, and we claim that our work is the first one which combines the two characteristics and sees how real-time we can get whenever we use state exchange. So that leads to the question of where do we store the state. We have a whole range of options. We have a whole layering. We start from in-memory storage, which only works on a single instance of a function. So as soon as a second function instance comes up, we will lose that data. We can go to local disk, or we can go to slightly affine, function affine storage options, such as durable entities that were at the time coming up. Azure functions have been supporting that for some time, and now recently also Cloudflare workers have been supporting durable objects. So we see more and more of those storage options which have certain characteristics. So if we look at just the Azure durable entities, which were available at the time of creating this presentation, we see that they are cost effective. The extra pricing as opposed to external storage such as databases is can be ignored. The second characteristic is the size limits. It's appropriate for modest amounts if we want to store game state, for example, if we want to store smaller amounts of data. And the main challenge, of course, is eventual consistency. That means In a game where it is quite decisive, where a player is located or where a certain action has been taken, we need to be sure that there is consistent state across all the views, and that can be achieved or at least almost achieved by a certain frequency of polling. So the more we poll, the closer we converge to a shared state, but of course then the more costly it becomes. So it's a nice trade-off. We can see how much we can come towards it. Another interesting aspect here has been the decomposition of the game. We have been thinking of creating, for example, a player function, and then each player would get a function and they would interact, or we transpose the whole decomposition, so each player accesses game state related functions, and this is what essentially was implemented with a very simple API. So each cloud function has several abilities to transform the game state depending on where the state is located. And so if we look at the results, we can see that the modification, the management of the durable entities was quite fast. Certainly in the sub 100 milliseconds range, which blends in very well with the original billing period that developers would understand from serverless systems. So there's not a whole lot of additional time needed. However, what is also, of course, the case is it depends heavily on the frequency. So if we look at a 3-minute game, which is a typical game of this type of Bomberman, we see that we have around 100 get game state functions. So we poll very frequently per second, and that translates into around 18,000 events. So each player in a 2-player game here has to pay around 0.4 US cents. And the storage itself, as you can see, does not really add up much. So that one can be ignored. Possible optimizations could still be applied. So the get game state function here, which synchronizes the game state back to each player, has been transferring always the full game state, which for a small game field is probably appropriate. As soon as the game state is becoming larger, let's say the game field is becoming larger, and then of course if there are just a few players around, it's like a sparse matrix. So we can think of a graph representation, or we can think of delta transfers to optimize that further. So what is the follow-up story to that? Because that project has been concluded a couple of months ago. We are now trying to generalize the findings. We are looking at other durable options, such as the Cloudflare workers model. Other cloud providers have also or are about to introduce similar storage options, and we also look towards creating those optimizations. And then the findings from that, of course, relate not only to gaming, but relate to any architectures, to any application models which are based on certain heuristics and based on the eventual consistency, which I think has been coming up in a couple of talks already today. So that concludes my talk per se. I have both the slides and a video which compares the 2-player views linked in the talk description on the WOSCx website. If anybody's interested, have a look there. And if anybody's interested to join, of course, in the upcoming work around that, also please let us know. And thank you.
Thank you, Joseph. Sebastian?
Yeah.
Can you share your screen?
Mm-hmm.
Looks good.
Okay. Thanks, Joseph, for demonstrating the use of our platform. I'm going to continue from there, and it's actually very interesting to see what you did with it. Okay, so the agenda for me today is to talk first a bit about motivation for serverless workflows and what we think, why we think this is important. And then I'm going to talk more about a new backend for the Azure Durable Functions, which is more efficient for executing workflows, in particular in terms of throughput. So first, serverless, I think it's always about developer productivity, about simplifying the development by delegating server management. Of course, this audience know it. Some people disagree about whether this should be delegating to a commercial provider or just your lower layer of the stack. I think it doesn't really matter which version of this you prefer. In either way, it simplifies life for the developer. I think to me, what's interesting about functions as a service and sort of the promise serverless, it's not just another service. It's really the way that you can compose services, which is a little bit different than just seeing it for like this source of, cheap parallel compute. What I mean by that is what we see users do often is that they have some services that already exist that they're buying, or have already built, that already have the auto scale and pay for use property. And now they need to compose them in a way while preserving this property. So this ability to preserve the automatic scale and pay for use property is really why they need it to compose services, which I think in this day and age, composing services is kind of the standard way of building things. And when it is stateful, when state is involved, I also need to add storage, which is also auto scale and pay for use. Now, while this story is really a good driver for serverless adoption, there's also problems with the use of storage. And the thing that we see are just really hard in general is the correctness aspects. So execution progress, you have to think about failures of functions. You have to think about timeouts. Persisting the application state has to be done through storage accesses because you don't have local storage in functions. The exactly once processing keeps being a problem for users. Functions can fire multiple times for a single trigger. That is just a fact that comes in from distributed systems principles. And developers must make these functions idempotent, which half the time they don't even know. And even if they know that they should do that, they don't get it quite right. And this can all be a problem. Concurrency is also a nightmare. Concurrency control is not a feature that is available in functions as a service. So you have to do it through storage, which is very difficult again. So I think that the solution to get those workflows working is to not have users explicitly, address storage from within functions, but to raise the abstraction layer and have a programming model that sort of reintegrates storage and compute a bit more again. And then this way, this will make it easier to use it for composing services. And we call this serverless workflows because even though it's not exactly the same as workflows in the past, it's still the best word we can think of describing this space. And I think we anticipate that this really will be the main way in which people build services in the future. So there's two questions that sort of are separately important. One is how to express the workflows, and the other one is how to execute them. Now I'll go through quickly through the expression of workflows just to give you a flavor of sort of different things to do. So the original one was easy, functions as a service plus storage. So you have triggers. You can do a hello world in 2 pieces by enqueuing a message that then triggers a second function. So people do this a lot. It's not super easy to use. Now, a newer thing to do is using declarative workflows. It's actually very old. People have been doing this for a long time. But for example, in step functions, you would have some state machine defined in some declarative language, here JSON, and then this can be used to orchestrate function executions. Now, we are more excited about what's now called workflows as code, where instead of writing a state machine, you write something that actually resembles regular code and has similar semantics as regular code, but then executes in a way that it really does orchestrate the function executions. So this Azure Durable Functions is an example of this, and there's also other examples, just as temporal workflows or Ray, that have a similar strategy to approach this. I could, think it's coming. Now, this talk is more about what we did on the execution pieces. How can we execute workflows more efficiently? And of course, we have to give fault tolerance and distribution on elastic scale. That's the starting point. But what we saw in our existing backend is that there's an excessive storage traffic happening because we continuously have to persist the progress of workflows. And this persistence creates throughput limitations. So just to give you a reference on how we do this, we actually have a separation of front end and back end, meaning that we have this SDK, which gets translated into a message passing model. And this message passing model then gets executed on the back end. So yeah, you could yeah, so this is helpful because we can separate advances in the backend from advances in the programming model. Now, the new backend that we worked on, which is called Netherite, is solving the following problem. As I said earlier, the throughput bottleneck on the original DF implementation, this is the implementation that Josef was talking about in his talk that he was testing for the gaming scenario. The problem here that we have for throughput is that every time a workflow makes progress, there's a lot of storage accesses because messages have to be dequeued, instance states have to be updated, new messages are enqueued. So the number of these storage accesses adds up quickly, and you reach a limit of where the system cannot, handle that many storage accesses. So our solution to this problem was to develop a new backend which doesn't represent the state in storage in the same way. Instead, we're using more of a sharded database type of implementation where we partition all of the instances and tasks into static partitions, and these partitions are then hosted on available nodes. So this gives us the advantage that we can now optimize the storage accesses using database techniques. So these partitions communicate with each other through asynchronous ordered channels. Importantly, we don't need distributed two-phase commit. So inside each partition, there are also some interesting optimizations. So the first optimizations, as you might expect, is to use a commit log. So this allows us to commit many workflow steps using a single storage right. And this is the source of reduction of the number of storage accesses, which helps a lot. Another interesting optimization we can do is persistence pipelining. So by that, we mean we don't have to wait for a workflow step to be persisted before moving on to the next step in the workflow. As long as we make sure that this type of dependency is respected before we send any messages back to clients or to other partitions. And then at the bottom layer of this picture, we're using a key value store that comes from Microsoft Research. Also, a colleague of mine implemented this in the database group. So this key value store we use two pieces. We use one as an append-only commit log, and the other one is for checkpointing. The checkpointing piece gives us larger than memory instance stores. It also allows asynchronous incremental checkpointing, and we can load it quickly. So this throughput really was a lot improved for the benchmarks that were sort of on the workflow intensive side. So you can see here on the scaling, the bottom axis shows you the configuration. So 12 times 4 means 12 nodes with 4 cores each. And what you see essentially is that with Netherite, we get scaling roughly proportional to the number of cores, while the original implementation in orange just reaches some level at which it can lower them up. You can see at the benchmark on the bottom right, this one is CPU bottlenecked. So the difference is not as big because here it is not so much the storage that is the limiting factor. So the status of this Netherite backend is currently in preview. So we're about to have announced general availability. Yeah, and I will, yeah, you can give it a try if you want to find out. We also have research publications on this. So the Netherite work was published in VLDB 2022. This is to appear in Sydney later this year. And that's all I have for right now.
Thank you, Sebastian. Now I will share my screen because Javier, are you still with us? Can you hear me? Javier? You may be on mute. Try to see if you can unmute yourself.
Hello?
Yes, can hear you now. Okay, great.
Hello?
I'm going to share screen with your slide.
Perfect. Let me know when you have the first slide.
I have the first slide on. Serverless computing, challenges, opportunities, and beyond.
Okay, perfect. Perfect, thank you. Yes, so I will basically like to sort of present a few slides on basically our idea on serverless computing. As a sort of teaser, some of the things that we are, some of our views, some of the things that we are working on, some of the challenges, and also some things that, some trends that we think that are going to be next. But as organizers have said, I mean, I will be also very happy to, to continue and follow up on the next event, because I think this is, I think, very important topic. So yeah, next slide, please.
Okay.
Basically, we have already seen that serverless computing is a term that is skyrocketed. Now we have all big cloud providers offering such services, and basically it's one of the most, I would say, hot terms that you can now programmers search online, or cloud practitioners or want to know more about serverless computing, and basically we have projections of huge growth in sort of the market of these systems. Next slide, please. So basically, we have obviously the traditional advantages that the reason why people are so excited about serverless computing, that when you look at the cloud spectrum of services of computing, you have like the whole spectrum, right? You can go to bare metal instances, you can go to containers, you can go to VMs, but then if you want to go to essentially the lowest granularity, in which you are really actually sort of paying only for the computer that you're doing, you have to go into the serverless computing frameworks, and that's essentially the reason why many users, customers are very interested in that. The other thing is also that it can scale pretty well, and you can actually have bursts of functions, and that could that's a huge advantage as well, because I think it has been introduced before. I mean, sometimes you have some load that is completely unexpected. You cannot predict it, and then you essentially need to act fast. And actually, serverless computing is one of the most scalable, I would say, systems that we have now. Next slide, please. Now, another trend that is also shaping the cloud itself, and it's also changing the way we're actually building cloud services, and also it will definitely affect the Lambda services as well, is that we are essentially decomposing the software stacks, and we are essentially disaggregating them, and we are scaling independently. And then if you look at the cloud stack, in the past, we used to have these sort of good shared nothing architectures in which compute and storage was decoupled, but now we are looking at, mostly all services are actually now being completely disaggregated. Even from traditional, I don't know, more like a database world, we have definitely seen now very popular alternatives that like, I think Snowflake is an example, but like another example is, I don't know, Redshift with managed storage, that even in this area, they have been, looking into disaggregating the storage. And also, obviously, when you look at Lambdas, we have basically the same thing. We have basically Lambdas, and it's basically scale independently of the storage. And these are things that are essentially will affect the way we are building such systems. Next slide, please. And also, there's another trend in that you guys know it as well, and I think it has been mentioned before, for example, in the first talk, is that we are really generating a lot of data. So essentially, we are generating a lot of data. We don't know how to process that efficiently at the same rate as it is generated, and this is becoming obviously a big problem. So all these trends are definitely going to affect, right, the way we are building the cloud systems, and also definitely also how we are building the serverless cloud system in the provider. Next slide, please. Now, so to recap, essentially now we have tons of use cases of essentially serverless computing, and this is actually growing. Every day we see new use cases, potentially new use cases, or more customers that are interested in serverless computing. We're also looking at an independent scaling of compute and storage, and we have tons of data. So basically, all these things call for sort of I would say a bottleneck, and the sort of the first bottleneck that we have seen in our workloads. Next slide, please. Is basically that, and it has been shown this in the past with prior work, is that essentially with serverless computing, we actually have to ship the data, right, the state, because the functions are stateless, into the serverless computing framework, the service itself, and the lambdas. So the then result is that basically we have, especially the cases of workloads that are essentially reading a lot of data from the object store in this case, but could be done, well, could be reading from other sort of services which are hosting the data. The result is that we have these lambdas that are essentially waiting for I/O, and that's actually an issue. Next slide, please. And we have seen, we actually have some use cases and customers that actually have exhibited the same bottleneck, but just to make it probably to showcase that also prior work is looking into that, is that we can also see other companies besides Huawei that are also similarly exhibiting the same problem, that we have these lambdas, we have all this data, but we in reality we are basically spending a lot of time in I/O to the object store, which is basically the favorite place of our customers to store the data. Next slide, please. And also we have also other use cases, other customers that are interested in sorts of workloads that could be more traditionally being executed in a sort of traditionally on-premise manner or provision manner, that are also interested in doing analytics in a serverless fashion. And I also show here some results from prior work, or some work in AWS, some work in IBM, which I also have pushed into this area. In that, essentially in this kind of workloads, we have seen a lot of time basically being spent just on the moving the data, or shipping the data to the code, which is in this case is the serverless function. Next slide, please. So basically, one of the directions that we are very excited about is essentially to make our object store more smart, more intelligent, and basically besides providing more like sort of the traditional get and put, we're also providing SQL declarative API, but also a serverless API capabilities, so that some of the lambdas that are more data driven, data intensive, they can be actually executed next to the object storage. Next slide, please. And this is actually something that other competitors have also looked into that. So basically, the declarative API has been something that's been very popular since a few years ago, but also AWS last year already also started working in sort of pushing down lambdas close to the storage. In our case, a bit more, I would say, aggressive, because we are looking into placing lambdas within the storage cluster. But at the end of the day, the whole concept of basically providing, trying to unify basically the lambdas with the data that require. Next slide, please. And basically the idea of this sort of functionality is that we want to provide some capabilities, some templates for the customer, some ecosystem in which they can actually raise the level of abstraction, and customers don't need to anymore look into, I don't know, like get and put, but they can have higher level semantics, and they can also define their own, and we can create a sort of ecosystem that things that could be, instead of having even like a programmer doing this, we have already some templates for customers to actually use it. So I think overall this is a very interesting direction. Next slide, please. Now, there are some other challenges that, besides the sort of the data movement problem, that are related to serverless computing, and that we have also seen, and we are also trying to figure out how to solve them. Probably these are also challenges that you guys have seen in, let's say, computer systems. So basically, one thing is that if you look at basically our serverless computing system, which is called function graph, but if you look at other of our competitors, There is a limitation that there is no real pipelining, right? So basically, when you return some I don't know, some object back to as a result of executing the Lambda, and you want to basically make a workflow with another Lambda, essentially there is no that you can start pipelining. Basically, you have a Lambda that executes and then sends it to the other, and then basically the other Lambda executes, and basically there's no flow. But ideally, what you would like to do is that you would like to have Lambdas, and you would like to basically be streaming data and pipelining, right? So basically, the data as it flows through the Lambdas, and this is very, very true for especially the data-driven Lambdas that we are seeing that the customers are very interested on. And also that we have some, I would say that sort of infrastructure limit that forces us to sort of limit the payload, and this happens in all cloud providers. But ideally, in our case, we also have some limits of some megabytes or some size that you want to send to another. That the Lambda can output that. In reality, you just don't want to do that, right? You just want to stream the data and don't care about any limit on the object, right? So these are sort of the challenges that we are working on to solve, and actually they come from our customers, right? That they really they have this sort of problem, especially if you're dealing with big files, images, videos, big tables, all those things. When it's running in Lambda, it becomes a problem. Next slide, please. Another challenge is essentially a bit more, I would say, researchy, is that when we are writing a function, how do we know the right granularity, right? You might have a function, a Lambda, that is doing sort of a big Lambda, right? It's with a lot of logic, but maybe you would like to split it because it has different computation ratios, and basically you can scale the Lambdas differently. So that's a sort of problem that we are seeing, that if you know the domain very well, you can really and you have time to I don't know, do trial and error. Maybe you can find it, but sort of at the end of the day, I think it was mentioned before, how to ease the programmability and to the user. I think it would be interesting if we could help the customer to also write the Lambdas, or help the customer write the Lambdas and have these things into consideration, because it will at the end provide better performance, right? Because if we have basically in like a Lambda that is maybe doing a lot of work and it's not really balanced, then it could be a bottleneck that could be solved by simply decomposing the things and just adding more Lambdas to one of the parts that you have decomposed in the past. So yeah, so I think the efficient Lambda decomposition granularity is definitely an important problem. Next slide, please. Now, I'm thinking just a bit about beyond about how serverless computing will sort of be integrated into the cloud stack, and then how what will be essentially the future, the trends. So we're thinking that serverless computing will be a very good match for using heterogeneous hardware due to the stateless nature, right? So basically, you have the function, and you have some sort of well-defined API to get your data from, and the fact that it's stateless, it will be very good, to map into any sort of hardware, right? And we think that if you have a sort of self-contained function, this could be run anywhere. It could be run in a CPU, or it could be run in a smart NIC, and this is basically an interesting direction. The other thing is that we will see Lambdas being integrated much more into the existing provision services, and this is already happening, right? If you look at Redshift, or if you look at Snowflake, they're already supporting and communicating with the serverless computing framework. But at the moment, as a sort of, I would say, the integration is very the moment is very coarse. So I think, as I said before, I think learning from the systems help to exploit the fact that Lambdas can help you at absorbing a burst of compute. I think that's something that there will be the next trend, right, on this, right? First, maybe a simple integration of Lambda into the provision services, but how to integrate and use them and scale it. I think that will be the next step there. And also we're very, very, very interested in work on basically matching sort of traditionally, big sort of cloud services like your, data warehouse or your machine learning service framework into FaaS, right? So if you look at papers in SIGMOD 2020, like Starling or Lambada, or basically the follow-up work from ETH on machine learning on FaaS, I think that's definitely something that we are very interested on, and I think we're going to see many more cloud services that are going to use FaaS as a backbone, and for that we need to solve the challenges that I have presented before. There are some challenges that I think have been mentioned in the previous talk about concurrency that I didn't talk about, but I think definitely those are also, they need to be solved. How to provide, logs in sort of distributed Lambda fashion. But though once we start solving all these issues, we'll start be able.
Javier, are you still there? I cannot hear you right now. Okay, I think we were reaching the end of the talk anyway, so let's move on, unless Javier will come back. Let's move on to the panel. Pedro, you had a great idea to do something interactive for the panel. Do you want to show your screen?
Sure. I can share now. Okay. Okay, so I will propose you. Sorry, let me go here to my Mentimeter. Here, you can use this link. Can you hear me?
Yes.
Sorry,
Javier,
I get disconnected.
you disconnected, so we moved on to the panel. Sorry about it.
Okay, no problem. I was almost about to be done, so yeah, no problem.
Okay, so I just copied a link to the channel to WOSCx1 that the audience can use. So I'm going to ask you like some question, like what are the main challenges in serverless computing? So as you answer them, we can look at my screen. So please connect to the link that I provided here and just include your options.
I will also put that link maybe in the Zoom.
Yeah, probably we can add it because not everybody I think is contributing in. Yeah. Okay. So
let's see how it should be in live showing, right? As a
yeah. Okay. So
it seems debugging is winning for now.
Okay, so a little bit more time and then can move. Okay. So probably, yeah, we can give like 1 or more minutes to the audience and then we can start the panel.
Sounds good.
So, okay.
Maybe we can capture, or it will be the.
Yeah, I will probably copy later on that to the channel, and then yeah, we can finish now with that if you want.
Okay. So for the panel, we have all the speakers that are co-hosts, and we ask it.
Well, sorry, there is another question.
Oh yeah, okay, yeah. Why not? Yeah. Can you put that question into Slack channel and, or is it the?
I think it's the same link, but.
Oh yeah, I see it. Yeah. Okay, let's see. It seems hybrid is growing.
So there are no more questions, Alex. So yeah, probably in 1 minute, then we can stop and I stop sharing.
Okay.
But I will share these word clouds in a Slack later on.
Yeah, that would be great. I mean, let's see what people think about it. Like maybe can comment also. Are those the most of the top challenges we have? Right?
Okay.
Okay, very good. So,
okay, so I stop sharing and I'll let you continue. Alex, thanks. I will share these word clouds.
Yeah, so that is the last part of our workshop, which is, we want to give you opportunity to provide some feedback and, discuss about what was today presented very quickly. Please use that feature in reactions at the bottom. There is a button saying, raise your hand. So we would like to start first with the presenters. If you, want to say something about the either workshop or answer to one of those questions or all of them, please raise your hand, and then we, make you available. So, and if you cannot raise your hand, just switch your video on and just, or put a comment in Slack, and then, we make sure you have opportunity to talk. Anybody wants to talk a little bit? Okay. So now, I mean, this is the end of the workshop. So please raise your hand. Anybody? I mean, we have now on 29 participants. If you want to, ask any question or make any comment, this is the time, to do it. You can just raise your hand or start talking. We want to make sure everybody has opportunity. Vinod, go ahead. I can see you.
Okay, I found it interesting that in the Mentimeter word cloud that Pedro was showing, two of the top challenges that people identified are debugging and some combination of developer productivity or developer experience. Those are hard to quantify, and have people come across any way to quantify research in that space? That might be one reason why at least I don't see a lot of the literature talking about those problems. Are there like common metrics, or like how do people quantify developer experience or debugging capabilities?
Oh, I want to say only that I agree. From my own experience, it's when it works, it's great, but when it does not work, serverless can be very frustrating and hard to understand what is going on. Joseph, you have your hand raised.
Yeah, so I would like to talk a little bit about the topics we have seen raised. So there was something about Edge, about Continuum, about distributed FaaS. So we have seen, I think, a federated FaaS concept today by the FunkX implementation. The question is, what else is out there? What do you think is going to be a trend? Is it more academic work, or is it really something that you know, will gain the upper hand and going from those monolithic centralized FaaS platforms towards more distributed FaaS platforms?
I guess I probably have some thoughts on this. I mean, we're taking one approach. I think the other interesting thing is you're seeing a lot of different FaaS systems be deployed in different places, not just the cloud providers, but open WOSCx and Knatives and all the other ones that are being deployed. So it's an interesting, we're getting to an interesting sort of world in which, if you imagine many of the computing systems have those FaaS interfaces deployed on them, there's obviously an opportunity for some sort of meta level layer. And I have seen several papers where people have looked at sort of running functions across different cloud providers, etc. So I would expect we're going to start seeing more meta level function deployment, and we're going to start seeing interest in sort of the scheduling type questions about how do we provision resources, where do we send functions, given we're in a very lightweight world where we can dispatch them wherever. And I think we saw in the last talk that theme as well. So
thank you.
I can also maybe add from a perspective of Kalix, you know, that is built on top of Akka as an actor model, you know, and this is something that we see Kalix as now it's only an entry point. You're building something in the cloud, but our goal is to extend that continuum, you know, go to the edge, and everything in the end, I think it's around developer experience. You know, yes, it's bringing features, but making that simple. Because what we figured out is, yes, if you have things that are complex, and they will always be complex, that complexity needs to be abstracted. So a larger community can use it. When a larger community can use it, more ideas, more use cases come up. So that developer experience is basically only the door. So yes, we need to build stuff underneath that are complex, but that developer experience needs to be simplified. Also, for perspective of that continuum, you know, you should have one developer model that would extend in the edge, but not thinking about how you're going to extend, but just that developer model that does that for you in the back.
So actually a follow-up question, Alan. So like in the work you're doing, like how do you know that you are improving the developer experience? Is it kind of personal judgment? Is it user studies? You know?
Yeah, so yeah, first we have we have GA from last year, end of last year, and we were in the test phase for a year and a half, a different kind of, let's say, our customer base working on Akka application, but also outside of community, and everything now is more customer driven. So our intention is to move more to developer experience. Are we there yet? For sure not, you know, but that's our goal. You know, that's things we need to enable that, you know, that level of abstraction, that level of simplicity, but again, to be able to achieve that complexity in the end. As I said, we are not there yet for sure, no, but this is something that it's just a process, you know.
Okay.
Alec, can I also add some question?
Yeah, absolutely.
Yeah, for Alan, I would like to ask, I have one for Alan and one for Javier. So for Alan is like, are you offering this like Cloudflare in a managed environment, or the technology, I have to deploy this technology on my cloud or on a Kubernetes cluster. So are you a technology that it's deployed like in any cloud, or like OpenShift and things like that, or it's like Dapper that it's Microsoft, but it's also on top of Kubernetes? What is your approach? Are you offering in a cloud? It's just the middleware, or?
It's a platform as a service, so it's fully managed. So you just choose where you wanna have your services running. So you choose with the creating of the project, you choose which cloud provider you want to use and which region you want to use, and that's basically it. Everything else is provisioned underneath. So you just deploy your business logic. You don't care about anything else. So that's the idea. Currently, we don't have an option that you can deploy that somewhere. Of course, if there will be someone big enough asking for this kind of deployment, I think we will consider. But for now, the idea is, because we are driven with this simplicity and not just developer experience, also operational experience, simplicity, we are managing that. And it's going in that direction. But yeah, we will see how this will evolve in the future.
No, that's nice that you are reaching there. And my other question is for Javier, because I am very interested, like object storage is like it's becoming really popular and like a universal platform, and serverless was always about object storage. So these object lambdas, we have been researching them, and they are very limited. So and I was amazed by your proposal here, like really adding some data oriented layer. That it's probably, I don't know if it's close to the data, but it's really close to the object storage. And for example, Kalix is more data driving in the sense that it's giving you programming abstractions that are easy to manage, like data structures. But in your case, Javier, what you are offering is like task-centric functions, but that can intercept data. So how far can you go with that? I mean, because you talk about SQL and other things, but what is the potential? It's real near data computing, or I'm curious. Is this available?
Yes, that's a very good question. So yeah, so basically our idea is that we want to execute things close to the data, right? And I think that what people are usually doing, even from database work, was SQL, because it's declarative and you cannot sort of mess many things up, right? Because it's like you have a query and that's it. We also thought that we should extend that for also serverless computing. Imagine that you have a code snippet, like in Python, because you are doing some machine learning and maybe you want to do some feature extraction on some image, on some video, right? So our idea is that it will be also good to actually execute these things for the same reason, right? Close to the storage, meaning that within the storage cluster, the same as the idea of declarative. Now, if you look at the entire sort of cloud infrastructure, obviously you are going to have always the compute service available, and it's obviously it has much more resources for compute, right? Because it's the compute cluster. But what we think is that we should allocate some of the compute within the storage cluster, and if we have enough sort of cycles available, right? Enough CPU available, we can actually send those lambdas to actually execute within the storage cluster. Now, what we have available right now, okay, so at the moment we just have some sort of internal beta with some customers, but at the end of this summer, we should have a system which we call Data Plus, in which we can specify already some functions, and basically whenever you you can define your workflows that are data driven, and basically they will be able to operate at the data path. And at the moment, at the beginning will be very simple in terms of scheduling, and then we plan to make it. It's still in the R&D area, right? The more complicated things, but we want to investigate essentially where if we have a very complicated workflow, what makes sense to run within the storage cluster, what makes sense to run in the compute cluster, and basically how to make all that work.
Okay, thanks.
So we are getting close to the end. I want to make sure that everybody joined our Slack and also our mailing list. If you were, for whatever reason, not able to join Slack or mailing list, just reach out to us, and we will make sure you have access to it. And for the future, we are looking forward to anybody to contribute, or if you know some other people that may be interested, please encourage them to join our community, join our Slack, and join our mailing list. And we will be organizing next workshop, or hopefully more than one, and hope to see you then. This is the last call. Any other questions or things you would like to raise? This is the time. Okay, then I want to thank you all our speakers and everybody who helped with the answering questions, or anybody who actually helped with organizing it. We cannot make it happen if you do not support us. So please continue in Slack, post to mailing list, and we hope to see you again soon. Thank you.
Thank you. Bye.
Thank you all.
Goodbye.
Bye.
Bye.
Thanks, everyone. Bye-bye.
Bye.